Welcome back to dataArtist tutorials. I'm Carl, and in this video we want to do the final things we need to do in order to have a proper camera calibration. There's a lot of stuff on our agenda, so we would like to start with vignetting removal or flat field removal. Okay. After this we do some blur measurements, so we want to measure what is done to this image in order to make it blurry, so we want to measure the point spread function. And finally, we want to measure the lens distortion. Okay. First of all, this camera calibration procedure is described in a PVSC, in a photovoltaic specialist conference proceeding with this title. So if you want to learn more about this, just Google it. Okay. Vignetting calibration. Vignetting is a nasty thing. I will show you the effect of vignetting first. Let's open dataArtist and let's open a random picture, a random electroluminescence picture. What we see clearly is that the pixel in the middle of the image seem to be slightly brighter than the outer edges. And this example is pretty clear because it's a monocrystalline PV image. Basically every cell has about the same intensity, so it's pretty clear that there's something going on which doesn't really belong to what we would like to capture. So this effect is the effect I'm speaking about when I say vignetting or flat field. Flat field actually is this vignetting effect plus camera sensitivity and a few other optical things all together. And how to measure this thing, this is what we will do now. There's quite an easy setup in order to get vignetting fields without any big measurement things you need to think about. Okay, and it basically works with your with a mobile phone. Just switch on a homogeneous screen, maybe a red screen, and put it directly in front of your camera. Okay, this is all you need to know about doing simple vignetting corrections. It's not necessarily the best correction, so we measure vignetting not in our measurement plane and at another wavelengths and all these things. This is not very good, but it is still better than nothing, and the best thing is it's very easy. So let's take a look how these vignetting pictures finally look like. Okay, so this is what you get. Let's do it in full screen because why not? This is what we get for one exemplary vignetting image. The problem with these vignetting images is that even if we move our imaging device a bit, or even if we change the angle a bit, then the vignetting image would look a bit different. I can show you this. Just load exemplar a few more images into this current display. Let's check out the differences. So here you see what happens if we check the position of our device. So why do we get different results? The reason is that our homogeneous screen, our mobile phone screen, our LCD screen, our whatever screen, is actually not so homogeneous. Okay, we have difference up to 15%. We can't process this with our eyes, but it is there. So what do we do in order to get a proper vignetting calibration image from all these different images? Well, the simplest thing we do is we just average it, but we don't just stupidly average all the difference together. No, we do an intelligent average. How this average procedure works just is described in the PVSC proceeding. Okay, let's start directly with netting removal. For this, we need to mark all of our vignetting images. In this case, I just made 10 images, but I would suggest you to make at least 15 different images. Okay, and let's load them into dataArtist. By the way, for these tools you don't need to load the images into dataArtist. The library which is behind dataArtist can also load the images by itself. But because we like visual things and we don't care about 10 images being loaded in RAM, we'll just load them all. Here they are. And you see they are slightly different, aren't they? So now let's load toolbars, calibrate, and let's go to this toolbar. This is the tool that we actually need, the flat field removal tool. And it creates a flat field calibration map from multiple input images. Okay, this is what we want. it also asks us for background image, and this is indeed a needed thing we need to do in order to do a proper vignetting removal, because this image also has a certain offset and also hot pixels. So the best thing you could do is you just take a background image which is even taken at the same exposure time or calculated for the same exposure times. In this example I will just take one background image in another display. And here's our background image. So let's link this background image to our tool. Okay, we have two different methods in order to get a flat field image. One method is from calibration image, and by the way this is what I would say is a calibration image, and the other method are normal images, because the nice thing about flat field is it's very simple. It's a very simple phenomenon. Okay, it's bright in the middle and it's dark outside, and you can describe it through a function which for example is described by Kang and Weiss, the so-called Kang-Weiss function. But about this I will speak later. Let's execute this function. The result will be one average vignetting array, average from all these 10 images, and it will have less noise and it will have none of these like different issues. It is also scaled between 0 and 1, because we multiply at the end, actually we divide our image by this flat field image. So this means that areas that are normally brighter will get normally darker at the edge will get brighter through division with this flat field map. Okay, so you see the noise level is much decreased. We also see our different camera sensor issues. The center is nice in the middle and so on. This is a good vignetting field. A vignetting field we can use in order to update our camera calibration. At the end of the last session I saved the first two calibrations that we did in a calibration file that I will load now. I called it test calibration. Okay, this is the current date. This is our info. We call it buy more cheese. Okay, and this is actually information that is needed, the light spectrum information. This light spectrum we actually measured in IR, because we had an IR filter in front of our camera, and this will be representative for the infrared light spectrum. Okay, let's go to our calibration. You see in light spectrum IR we have dark current, flat field and noise. In the visual spectrum we have nothing, because there's nothing in the visual spectrum measured so far. Okay, this is how you get the vignetting field from calibration images, but as the real life so often is, sometimes we don't have these images. We just have EL images and we need to correct them somehow without having extra calibration. So these images are images that I will use in order to extract the vignetting field. Let's mark them all. Load them. Okay, so these are complete random pictures, and you see every time it will be somehow brighter in the middle and somehow darker at the edge, but you see intensity and whatever we want to image, it's completely different. But we still can extract something like a vignetting image. It depends strongly on your data quality. So if your images are very similar, then the vignetting field will be also more representative. But this is just for demonstration purposes. So now we go to the method from normal images, and we say we want to fit the result of these average images to the vignetting function or to a polynomial. I would suggest you use the vignetting function. Normally the result you get out of it, it's a bit better. If you even have not a background image, well, we can extract something like the background from the EL images itself. So let's see what we get out of it. And here we go. This is the flat field that we extracted from these different images through an intelligent averaging, smoothing and fitting procedure. As you see, the center is not exactly in the right middle. When we use the calibration image, it was pretty much in the middle. Now it is not, so you see the quality is not so good. So I'd say I don't want to update the calibration, but actually I want, because then we can decide which we want to use. Do not use bad quality light spectrum SIR. And now we can go to our calibration file and we can actually change which flat field version we want to have. In a second, there's a small bug because we have the same date and it can't display the same date as two different entities. So I'll update it again and I say this was from yesterday. Okay. So now flat fields. This is the one that we don't want to have. This is the one that we use. Actually it isn't. But you get the point. Okay. Vignetting, I'd say we are done with this. The next thing is the measurement of the point spread function. So over the last 10 years people came up with a lot of more or less creative methods to measure the flat field. Some of them are very complicated, some of them are quite not flat field, what am I saying? The point spread function. Some of them are quite complicated, some of them are quite easy. I won't tell you much about them because at the moment in dataArtist there's only one method embedded to measure the point spread function, so the blurriness of our image. Okay? And this method only works if you actually measure PV modules. If your image cells, then the dots that we use in this method need to be much too small, and it's much too big a pain actually to make these dots. So what we see here is an EL image, and in the middle there is a mask on top. Okay, this mask actually has a lot of tiny little holes. Okay, these holes were done with a needle. Okay, these pinholes. This needle was taped, and every time the needle was put in around about 2 millimeters through this paper and created these pinholes. Then this paper was taped on some glass and everything was put on top of our EL images. So the nice thing is that we see here is a direct measured point spread function. So as long as the pinholes are much smaller as our image pixel, what we see here is actually representative for point spread function. As you see, they all look a bit different, but if we just average all of these pinholes together and correct their position, then what we will get out is a pretty accurate assumption of the actual point spread function. So, well, let's do this. This is the tool we would like to execute, the point spread function tool. And in order to execute this, this is the method. As I said, it's only one method embedded at the moment. We need to set some boundaries because, well, we don't want to measure the point spread function here because there's nothing to measure for it. So say, okay, we're only interested in this area here. Don't have to be very precise about this because it doesn't matter whether one pinhole is in there or not, because we have so many pinholes in there. I think about 160 or so. Okay, we defined our boundaries. You can show and hide them. And if we are done with this, actually, I would like to draw the found points just to show that the program found everything. Let's activate the tool. By the way, if you want to activate the tool, you can either click on activate here or you directly click on the tool itself. Zoom in a bit and we see, so program found most of our pinholes and put a circle around it. And from all these different found individual point spread function and calculated one average point spread function. Okay, so this is the tiny spot in the middle, and what you see around is actually noise. Interestingly, it's a bit brighter in the dark than it's in the top, but this is because of light which came basically from our device. It is not properly shaded, so this is basically noise that I would like to exclude in our point spread function. To do so, I first say I don't want to, wrong button, I don't want to set these two things. Okay. And now I will filter low values. Remove them. Okay. And here we are. Now that's maybe a bit too much. Okay. Let's Go back to the full scale. Okay, this is our point spread function. And since we are done here, we can update our calibration. Bad calibration, because, well, I'm not very fond with this point spread function, but it's better than nothing for the moment. We are in infrared, and we just updated our calibration. Now we have an entry for the point spread function. Very good. Image deconvolution dataArtist is embedded using two different functions from the SK image package. One is called supervised VNer and the other one is just called VNer. The supervised VNer method just uses the image and point spread function, so the array that we basically just measured. The nice thing about this supervised VNer function is it needs nothing else. But the problem with this approach is it is quite slow because it is an iterative process. So much faster function is the pure VNer function. VNer function. Problem with this function is it needs an extra value, so-called balance value. This balance value tells us how strongly we should do this deep blurring algorithm. Okay, a balance value of 0 says we deep blur a lot, a balance value of 1 says we deep blur not much at all. If we set this balance value, deep blurring images will run much faster. So because we like fast things, why not just decide about this balance value? To do so, we will deep blur this image in different balance steps, and then we will define about the balance value that we like the most. Okay, because we don't want to deep blur the full image 20 different times, because it would take some time. We will say, okay, we actually only care about a smaller area in this image. Let's say this area. Okay, now let's load our deconvolution balance tool and say, okay, we want to vary this balance value from, for example, this value to example this value, and maybe we want to have a look at 15 different deconvolution steps to see which of these balance value is the best. First, it needs a calibration file defined, so let's load one in order to get the point spread function from this calibration. And then after a few seconds we have 15 different images created with different deconvolution parameters, with different balance parameters. Here you see that at the end it is still quite soft, and the smaller the balance value you get, the harder also gets the result. So here we have actually a lot of deconvolution noise, which is not very beneficial if we think about image quality. So we'll set up a parameter which might be here. So this is the balance value that we would like to choose. We go back to our origin display, the display that we used to execute this tool, and we say update calibration. This is the value we would like to have. The spectrum is infrared again. Hello world, and just done. And now we have new balance value, which is called hello world. It has this value. By the way, there was also an older value saved, which was this one. Okay. The last part of this video is about measuring lens distortion. For this, let's load a few images. The way lens distortion is measured in dataArtist is basically the way it is measured in a package called OpenCV. Lens distortion there is expressed as a quite simple transformation, a polynomial transformation in one side and this equation, and it's all brought together to one camera matrix, which basically consists of the focal point in x value, the focal point in y value, and the camera center, or the focal length, not the focal point. and also a few distortion parameters. We'll measure lens distortion with, again, importing our images into dataArtist. Here they are. And then executing the lens distortion button. For this, the tool needs to know which pattern we actually used, whether we use a symmetric cycle pattern, an asymmetric cycle pattern, or a chessboard pattern. If you would like to do lens distortion but you don't have these patterns, well then just click on the button Show Patterns, and then you can basically just print the pattern that you would like to use in order to do a proper lens distortion removal or calibration. Normally I like to use a chessboard pattern because it's more common to use. Okay, now that we defined the method or the pattern, we have to give the right number of corners in X and Y. Well, for chessboard it's the inner corners that count. In this length it's 1, 2, 3, 4, 5, 6 corners, and here it's 8, which is already set up. The aperture size is actually not very important for the moment, so you can ignore this. What we also would like to see at the end, we would like to see whether our algorithm found the chessboard every time right. Okay, so this is just an additional thing to see whether the algorithm worked as it should. Let's activate. After a few seconds, you will see all the detected chessboards as a color layer on top of our images. You see all positions were right detected, and most of the layers were actually used in order to get chessboard calibration. Here we see one didn't work out, but the others worked at least. Here we have our camera matrix, so focal length in X and Y, image center, and these are the distortion coefficients. We now only have to say after calibration, give everything a name and so on, and then update our calibration. And then we have everything we need in order to correct our images. How this is done I will show you in the next video. The last thing I would like to show in this video is another way of viewing multiple images. So you are used now to this time slide, but there are other options as well. We could, for example, go to a grid view. In this grid view we can see all of our images nice and next to each other. So if we want to see changes and we want to see them all together, this is maybe the view we would rather use than using the time slider. We can set up the right number of rows, for example 5. Go back and forth. And then we have the grid view in another view. Okay, so this is the end of the second camera calibration tutorial. As I said, the next tutorial is about image correction. Stay tuned. Goodbye.